In this video, we're going to look at decomposition of the serial algorithm we talked about last time. A simple way to identify concurrency is to look at loop iterations. For example, we have multiple iterations of the loop. Can we perform more than one sweep, more than one iteration concurrently? Unfortunately, we can't. We can only start the I plus first sweep after we finish the ith. The reason is that we're using the old values from the previous iteration and the new iteration, and so we can't do two iterations concurrently. Note that computation proceeds from left to right and top to bottom. I think we saw that last time. So when we compute a point, we use the new values from the left of the point and above the point, but the old values of the point itself and its neighbors below and to the right. A diagram is shown here that illustrates the dependencies. It shows that to compute the new values at a point, you use the new values from above and to the left, but the current value of the point and the old values, which is the same as the current value, from the right and below. Because you don't see arrows there pointing into that point, you know that they don't use those new values. Now, the horizontal and vertical lines with arrows illustrate dependencies. This point, for example, depends upon the old values from above and to the left. The dashed lines along the anti-diagonal connect points that have no dependencies because the calculation of none of these points depends upon the calculation of any point on a different anti-diagonal. Of the order n squared work in each sweep, there is concurrency proportional to n along the anti-diagonals. So let's consider whether we might exploit this parallelism. Well, one thing we could do is leave the loop structure alone and let loops run in parallel, but synchronize calculations at each point to make sure that the new values above and to the left have been computed before we compute a current point. Why isn't this a good idea? Well, this means we have to synchronize at every point, and so the overhead of synchronization operations will be too high. Another thing we could do is to change the loop structure to allow the outer for loop to iterate over the anti-diagonals, in other words, like this, and the inner loops to iterate up the anti-diagonals. Why isn't that a good idea? Well, in this case, the load would be unbalanced because the first processor to start has only one element to compute along its anti-diagonal, and the processors that are in the middle have 2 times the square root of n points to update, and the processors at the end, again, only have 1 or 2 points to compute. Also, we'd still need to synchronize between the anti-diagonals, and that would impose some overhead. Well, note that the Gauss-Seidel algorithm doesn't require us to compute from, the top left to the bottom right. This is just a convenient way to program on a uniprocessor. We could compute the points in another order as long as we use updated values frequently enough. And so that suggests an ordering that's called red-black ordering. And we're dividing the points here into alternating red and black points. And you can see that that they're offset by 1 between the rows, so that if we're computing a red point, we're using only black points as neighbors, and if we're computing a black point, we're using only red points as neighbors. So this would suggest that we could do a red iteration and a black iteration in parallel, which means that we compute all the red points and then we compute all the black points. Well, this looks like it might not be so efficient because we don't use any updated black values in computing red points. But on the other hand, we use all updated red values in computing black points. So it might or might not converge faster. It depends upon the problem. But it does have advantages for parallelism. That's because we can compute lots of points in parallel. How many red points can be computed in parallel? Well, all of them, and there are n squared over 2 of them. How many black points can be computed in parallel? All n squared over 2 of them. Red-black ordering is effective, but it's a little bit harder to consider in this lecture because we can't show all of the code on a single screen. So let's consider a simpler decomposition, and that just says that we ignore all dependencies between grid points in a sweep, which means that if one processor gets ahead of another processor, it'll update all its points before the processor below updates any of its points. And so that process may be using more updated points and the other process may be using fewer updated points. But that doesn't really matter because on average about the same number of updated points will be used. In this case, a sweep just updates points based upon their nearest neighbors, but we still have to use global synchronization between sweeps. Now, execution is no longer deterministic because the number of updated points may vary from run to run, but for most reasonable assignments of processors, the number of sweeps won't vary too much. Let's look at the code for this. We see here that we have the outer while loop and two inner for loops. This code looks exactly like the code that we saw before, the only difference being that the inner loops are replaced by for all loops. So instead of for loops, we have for all loops, which means we can compute all n squared elements in parallel. We could write the program so that computation of a row had to be assigned to a single processor, and that would be a very small change. All we'd have to do is replace for all in the inner loop by for. Now with each row assigned to a different processor, each task has to access the elements above and below it. So it has to access about 2n grid points that were computed by other processors. Meanwhile, it computes exactly n grid points itself. So this makes the communication to computation ratio order 1. That means that there's a lot of communication per unit of computation. So we'll look forward to simplifying that.